So as you already will have guessed from the session and the paper title, this talk is about key exchange. So key exchange is this neat concept that allows two remote parties to establish a shared symmetric key over an insecure network. Usually you bootstrap this from knowing public keys or certificates of each other, and you will run a protocol, the key exchange protocol, which in the end is supposed to output a shared key, the same key on both sides of the protocol participants. Security-wise, formalizations go back to the seminal paper of Bellar and Rogaway from 1993, and there are two main security goals that you usually consider here. The first and probably most intuitive one is key secrecy. So key secrecy is basically telling that an outsider adversary, Eve, to that communication, given some capabilities formalized, should not learn anything about the key. So basically the key should be as good as fallen randomly from the sky, being perfectly random on both sides, and Eve not knowing anything about it. The other property is authentication, and it's often formalized in an implicit way by giving, for example, Alice the guarantee that only Bob can potentially hold the key, and no one else. However, Alice is not guaranteed whether actually Bob indeed holds the key or not. She's just told that if only, then Bob can be the one that holds it. So this is where key confirmation comes into the game, the topic of this talk. And to start with an informal definition, let's quote from the Handbook of Applied Cryptography, where it says, key confirmation is the property whereby one party is assured that a second, possibly unidentified party actually has possession of a particular secret key. In other words, it's basically aiming at saying that you're ensured, Alice is ensured, that Bob actually holds the key that she has. So while this property key confirmation is often mentioned in scientific papers on key exchange, interestingly, there was no formalization, no explicit formal treatment of this notion so far. So you may wonder whether key confirmation at all matters, where it's important to look into it. And if you ask cryptographers, one answer you might get is, well, actually, it's not so interesting after all, because if you have a key no one else has, and you encrypt something under that key, well, no one can decrypt it, but that's not a security problem, so why should you care about it? You might also think, well, it's somewhat clear when you get key confirmation. You just use the key, you encrypt something, and by that you prove that you hold the key, and the other side will know that you have it. However, one needs to be cautious here, because if you do this in a careless way, you might actually lose the main goal, security goal of session key secrecy that you wanted to actually aim for in your protocol. So cryptographers usually go and say, okay, well, you just derive some separate key, which is independent, and then you send some message authentication code over a transcript to confirm that you are sharing the same communication. And if you look into standards, it's interesting that in the discussions around TLS 1.3, the upcoming next version of TLS, there was some discussion whether key confirmation is actually something that should be explicitly aimed for. And TLS 1.3 settled for it, so key confirmation is a goal for TLS 1.3, and it's also mentioned as an explicit goal in various NIST standards, for example. So there's some good reason to look into key confirmation, and what we do in this work is we do three things. The first one, we provide a formal model, a formalization of what key confirmation means in order to provide a ground where you can have well-founded discussions upon. Second, we look into this folklore transform, refreshing with a new key, sending a MAC, and analyze what kind of key confirmation properties you get there. And third, we look into one of the latest drafts of TLS 1.3 and check what key confirmation properties are established there. So let me start with the formal model, of course, in a more high-level way here. And there, as you will see in a second, there are actually two notions that we formalized there, and I'll explain you a bit why. I'll start with what we call full key confirmation, which is supposed to formalize the intuition that by now maybe you already have. Which means that if one side, one session accepts a key, then there should be already another session which holds the same key. So consider a protocol where Alice sends a first message which allows Bob to derive a key, and then Bob responds with its message, and then Alice concludes by deriving the key as well. So now full key confirmation is formalized through the following, establishing the following predicate or ensuring the following predicate, which I'll translate in high level. So you're guaranteed that for any session in a particular set S, and here you might think of S being the set of all client sessions in the protocol, when such session accepts, there exists another session S prime in another set S prime, for example, a server session, that ensures satisfies three properties. It accepted already. It shares, it's the communication partner. It's like having the same communication transcript, for example, or here formalized as holding some identifier value for this session. And most importantly, third, it holds the same key. There's actually some technical restriction that we need to add here. We can only talk about key confirmation when you're communicating with someone that you know in particular, which is not the adversary, because formally you cannot reason about whether an adversary derives a key or not. So that's now formalizing this intuition that when you accept, there is already someone that accepted with the same key, so you know you're not using the key for nothing. And interestingly, this formalization now exposes a nice duality to the classical notion of authentication. So remember that implicit authentication tells you that there exists at most one session that holds the key you're talking about. While now full key confirmation says that there exists at least one session that holds the key. This means that these two notions are quite modular and combine nicely. You can prove them separately, and in a combined fashion, you will then get that there exists exactly one session, namely one of the partner you wanted to talk to, which holds the key that you are holding, sometimes called explicit authentication. So why a second notion? Well, this is because you inherently cannot have this notion of full key confirmation on both sides of the protocol run. Why is this? Let's look at an example. So let's say there's some communication already going on, and then at some point, Alice accepts the key. She sends a last message in the protocol, which makes also Bob accept the key. Now, in any reasonably strong model, an adversary is always allowed to drop this last message, to infer with the communication, drop this message, preventing Bob from deriving this key. So in particular, Alice cannot get this guarantee that when she accepts, there is already someone that holds the same key. In any particular, whenever you're the sender of the last message, you can only get some weaker guarantees. And this is what we formalize under the notion of almost full key confirmation, which aims at the following intuition. The guarantee for a session is when the session accepts, then there exists already another session that might not have accepted yet, but if it accepts, you're guaranteed already that it will do so with the same key. And for this, we introduce a technical helper tool, which we call key confirmation identifiers, and which work as follows. Let's look at this example. So let's say Alice sends a message, and then this provides some agreement already, which allows Bob to send a key confirmation identifier. I will show you in a second how this then works out in the formalization. Then Bob responds, which makes Alice also set this helper tool key confirmation identifier, as well as accept the session key. And then if Bob receives Alice's last message, we'll also accept with a key. So now the formalization, again translated in a more high-level way, saying that for all such session like Alice is now on the left side, when it accepts, you're guaranteed the following. There exists another session already which shares some agreement. Namely, it has set the same key confirmation identifier. It doesn't have the same key yet, it might not have accepted yet, but it holds the same key confirmation identifier. And in particular, when this session accepts, you're already guaranteed that it will only do so with the same key. So you cannot make this other session accept anymore with another key. So of course, there's a lot more things to formalize, and I refer you to the paper. One thing I want to mention is that these two notions are indeed comparable in the sense of that full key confirmation is stronger, that is, implies almost full key confirmation. So now let's look how these notions can be applied to protocols. I want to first look into this protocol transform, which is supposed to add key confirmation to some arbitrary protocol. So we start from a key exchange protocol, which is complete in its sense. It outputs a key and some session identifier, which is basically like a notion that makes you formally link these two sites together as talking in the same communication. You might think of it being, for example, the transcript of all messages exchanged. Now we want to build around this a transformed protocol which ensures key confirmation. And we do so by, first of all, having this session identifier agreement of the initial protocol being our key confirmation identifiers, our preliminary agreement. And then from the session key that we derived in the main protocol, we derived 3 independent keys, a green one, an orange one, and a purple one. And the latter 2 we use to exchange message authentication codes over the transcript or the session identifiers that establish the linking in the original protocol. And if these verify, we then output the 3rd, the green key, as our actual session key, which will be independent of all the other keys involved. So now in the work, we show that, first of all, this transformation doesn't break anything. So it preserves, in particular, the key secrecy and the authentication properties of the original protocol. And moreover, it provides you with the strongest key confirmation you can hope for, namely full key confirmation for the receiver and almost full key confirmation for the sender of the final, of the last message. All right, so now let's look into what key confirmation, what we can say about key confirmation in TLS 1.3. More specifically, we looked into draft 10. This was a version out there around October, following October last year. And we look into the main handshake, which is a Diffie-Hellman-based handshake, so key exchange protocol in TLS. And you don't have to know or understand all the details of the protocol. The main ideas of this handshake is as follows. So the client and the server start off by the client beginning, the server responding with a hello and a key share message, where the hello message is basically a random nonce number value, and the key share being a Diffie-Hellman share. And then for authentication, the server will send its certificate, in particular including its public key, and a signature over the transcripts of the messages exchanged. It will then also send as a finished message a MAC value over this transcript. And then to complete the handshake, the client for authentication also sends its certificate and a signature and MAC value over the transcript. What we can show now is that this basically achieves the strongest key confirmation you can hope for in this setting, namely that for clients which send the last message, you get almost full key confirmation. So you don't know whether the server actually will get your message. It might be dropped. But if it gets, the server will accept with the same key that you're having already. On the other side, the server gets full key confirmation. So he's already sure that there is a client out there which holds the same key. Interestingly now, we show this based on the signatures in the protocol, not based on the MAC values sent, so the finished messages, which are somewhat resembling this generic transform, which might be a bit surprising because often finished messages are thought of the mean of getting key confirmation. But we can actually show that even without key confirmation, the same properties hold. Beware now, this does not mean that we advocate removing finished messages. Hell no. It just says, OK, you get this from some other parts of the protocol already. In particular, the finished messages are quite important for other modes and for other aspects of security in this protocol. But for key confirmation, you can actually rely on the signatures. And finally, in the paper, we also look into the unilateral authentication case, so the case where only the server authenticates. And we show that we get some somewhat similar results there. Refer you to the paper for this. OK, so to summarize, well, we formalize key confirmation and are the first ones to do so in a game-based setting, providing some formal ground for discussion of this property where there was none before. And we establish separate two notions, full key confirmation for the receiver of the last message, and some weaker notion, almost full key confirmation for the sender of the last message. We then exercise this formalism on this generic transformation and show that it indeed generically adds key confirmation to some key exchange protocol. And finally, we look into TLS 1.3, and we show that it provides key confirmation, interestingly, even without using the finished messages within this proof. All right, this concludes my talk. Thank you very much.
Thank you. Questions? So I have one question. So you say the TLS provides key confirmation without the finished messages. Does that mean that I can completely remove these messages and the protocol is still secure? You lose nothing, or you lose something else?
So again, I want to stress that one has to be careful here. So for key confirmation in this main handshake mode, you don't need the finished messages, and we show that you could even remove them. However, this does not say anything about what kind of other properties, key secrecy, authentication, etc. you get. We don't look into this for this specific purpose. And in particular, we do not advocate to remove them, but especially because they serve important purposes in other modes of the protocol. So for key confirmation in the main mode, you don't need them, but please don't remove them.
Okay.
I have a question. So you mentioned that some TLS modes don't use signatures. Did you look at key confirmation property for, let's say, pre-shared key in TLS 1.3?
No, we just looked into the main mode using signatures. For the pre-shared key mode, you're right, there are no signatures involved. This would be in particular a case where, well, A, you get secrecy only through the finished messages, so you crucially need them. And I would expect that you also get key confirmation only through these messages.
Thank you.
You're welcome.
Okay, last year's best paper was the Berdouche paper on TLS on the previous version. And they pointed out that the implementations were deeply flawed. I applaud what you're doing in starting to get the formal analysis of the protocol. But ultimately, I think there are a lot of properties that the Berdouche paper showed should not exist. And these are the tough ones to get at. So I just wondered if you had any thoughts about where this is going and what you might do in the future. And this question sort of bears on some of the subsequent papers in this session as well, but I'm not going to get up and ask it each time. So go ahead.
Well, I guess the others can just repeat the question without being asked. For my work, yes, I fully agree. Of course, this is just one piece in a large puzzle. There are a lot of things to look into, both from the theory perspective as well as from implementations. And yes, the paper last year did a particularly great job there in finding some aspects. And we're definitely not done. I think it's worthwhile and rewarding to both look into the theory aspects and to transfer them then into further models which are closer to implementations.
Matt Van Gundy from Cisco Systems. I'm trying to remember way back, but if I remember correctly, the Bellare and Rogueway model is actually broken by key confirmation. The adversary can use the attribute of key confirmation to distinguish a key from a random key. So I was curious if you could comment on your security model and whether or not you looked at how key confirmation actually affects that model.
I'm not sure I got the question right. I understood it as you're saying that in the Bellare-Rogueway model, key confirmation you inherently cannot have because it breaks the key secrecy aspect?
Basically, I don't know if it's necessarily an important, like the adversary can recover the key, but it actually does provide a way for the adversary to distinguish from random, which is essentially their security property.
Yeah, okay, so this notion is compatible in the sense of, well, the main point is you cannot do key confirmation with your main key, like sending a MAC under your main key. This breaks the key indistinguishability in the sense of Bellare-Rogueway. So what you have to do, and this is what's done, for example, in this transform, you derive a separate key. With this one, you do key confirmation, and the other one that you kept indistinguishable, not used before at this point, you output as your main session key, and then you still get like the freshness, the good property in the sense of Bellare-Rogueway.
Cool, thank you.
Welcome.
Final question?
Yes, interesting work. I was wondering, have you come across protocols that are used in practice or being standardized that do not meet your definitions of key confirmation?
Well, in particular, if you look into TLS 1.2, there was quite some trouble in analyzing TLS 1.2 in a formal way because it did not fit this concept of having a fresh key at the end of the handshake. So you needed more tailored, more specific ways of analyzing it because it broke this idea of not using the session key before you finalize the handshake. And that's not the only example, of course, but it's one of the prominent ones.
So it's not clear if the protocols that do not necessarily meet your definition, but this work helps you sort of organize the discussion about it.
Well, we didn't look into whether TLS 1.2 meets this kind of key confirmation notion, but it's an example where using the key in a way where the key was used in a way that breaks this main idea of key secrecy, 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 idea of